So, let us write down the, so this Fermi sea is an important concept. So, basically Fermi sea is like Dirac sea, but they are not infinite particles, but you just keep filling up till it reaches the maximum. So, there are n particles, then I just keep filling them one by one. Okay. So, you might have seen this picture, no, this is the Fermi sea. So, the highest level, so I keep filling up, no, this so you can think of particle in a box. So, the every box has a energy levels, right, by quantization, and keep filling up, then highest one will have is momentum. So, that is P f square by 2 m is energy, and this is called chemical potential. Okay. So, this energy is filled up to here, E Fermi. I am sure you have seen this in the course. So, I do not want to really repeat it, but just for completeness I am doing it. So, particle below is filled up with Fermi sea, and we write down Fermi sea as this. I create particles, I create basically electrons at all these level below Fermi sea, right? This is what it means. Vacuum was nothing, I create particles at all these states up to P f, okay, and these are in a particle in a box. So, these are free particles. So, you just like a keep filling up in 1D, of course, is, you know, that is a levels run for 1D we create that, what is, I don't know if I get n squared energy, okay. So, in 3D we have nx squared plus ny squared plus nz squared times h bar squared by 2 pi, okay. And so, these are number of particles. So, that is the name, that is so well, chemical potential has a interpretation, how much energy is required to pull a electron. So, the top guy will be pulled up, and that is same as E P f square by 2 m. So, yeah, you will pull the top guy only, no, that is so that is the interpretation, and that is coming from the definition of free energy, no, sorry, chemical potential. Okay. So, free electrons basically they said we write down Hamiltonian. So, as sum of particles, well, basically energy of the particles with energy positive. So, this E Fermi, the one above that, well, positive means above mu. So, this is energy bigger than chemical chemical potential, and these are energy below chemical potential. So, E alpha is defined as energy minus mu, okay. So, this is for the particles. So, the free particles which are conduction band electrons are these guys, the holes are below, these are holes, and they have negative energy. So, this is how we write, this is P square by 2 m minus mu, this is that one, and this guy is this one, okay, and these are holes, okay. Now, we will not get into this, but this is how this whole many body framework is created. And charge, so if they have positive charge, then they have negative charge, they are basically they are not quite antiparticles, but they are interpreted as antiparticles, kind of, well, they are not antiparticles. In relativistic field theory there will be antiparticles, but in these are called quasi particles. But they are negative charge, but mass need not be just equal and opposite, okay. There are certain complications, okay. I myself do not know full details about this, but so these charges are basically coming from here, q and minus q, but mass is not necessarily just equal and opposite, okay. Okay, so a few last comments. So, bosons and fermions, they are fundamentally different particles, okay. So, simple thing is, for bosons operators commute, for fermions operators anti-commute, okay. For bosons no negative energy states. So, for bosons we do not need to create a Fermi sea, okay. There is a bound which comes from this algebra, nothing required to fill up the stuff, but for fermions there are negative energy states. Okay. Fundamental bosons do not have antiparticles, but fermions have antiparticles. Okay. These are part of particle physics, and there are a lot of discussions on it, but I am just giving you a very simplified picture which helps clarify this stuff. And bosons Higgs mechanism, which we will discuss later, but fermions do not have Higgs mechanism, which will come later. Okay. So, important points, I think some my observation. So, this creation and destruction operators of particles are uncorrelated. So, look, this fermions are the wave function is antisymmetric, no. So, you may think that there are a lot of correlation, right, is not it? I mean, there is antisymmetry wave function, that means there is correlation between two electrons, but turns out yes, there is a correlation because of this its particle nature, that they have to be antisymmetric or symmetric, but this creation and destructions are totally random operations, they are not happening with certain order. So, what I am interested in is this non-equilibrium nature, is there some kind of energy transfers in these systems, or are there some kind of hierarchy system which is built in. So, you may know that Fermi-Dirac statistics, you consider the particles to be non-interacting and random, right, yes or no. I mean, this is how you construct the Fermi-Dirac statistics for free particles. Okay. Now, if they are interacting, then, or if they are correlation, then that should come in this distribution function, but we assume that to be not. And what is the origin? So, my question was, if they are antisymmetrized, then we cannot write down them as a random particles which is in statistical physics. You get my point? Boltzmann distribution, we assume the particles to be uncorrelated, random at a temperature T, but why do you assume the same thing for fermions or bosons? They do seem to have certain correlations, right, I mean they are antisymmetric or symmetric. So, what is the origin of randomness in fermions or bosons? And to me it appears that it is when it is created, or when these particles are there, though there is symmetry, but it is basically uncorrelated, which is a mystery. Well, this is not mystery, it is a very surprising thing that they are uncorrelated. Okay. In fact, the correlations we can compute, and they will be 0 for field theoretic correlation. Okay. So, these particles are in equilibrium, in quantum particles are 2 in equilibrium, like Bose-Einstein condensate, no, Bose-Einstein distribution, I am not saying condensate. Bose-Einstein condensate can have order because of interactions, okay, but at a finite temperature or a significant temperature, there is no correlation. Okay. So, superfluids or superconductors, they have interactions, and that brings in order, and that brings in non-equilibrium properties, multi-scale properties. So, we will explore some of this, which I am also thinking about them. In fact, that is one objective for me to explore this phenomena. Okay. So, let us stop here, and we can take some questions.